Okay, hey guys, welcome to Math 4000. This is week number four, sorry. So today we'll start doing combinatorics. We'll start a new chapter, and I will explain immediately what are we going to do here. Unfortunately, like you have seen, I tried to do some extra video lectures. And also we had some extra recitations last week. So if you would like to present some problems, we can organize an extra recitation for those of you who would like to present some problems and, well, I don't know, maybe you want to share the solutions to others. This week I'm going to do the same thing. Probably there will be another extra lecture recorded by me. I don't know, sometime maybe tomorrow, because it's, like I said, it's impossible for me to cover everything in combinatorics in just 1 week. So basically there is an entire semester of combinatorics, right? And I can only do, well, some basics. All right, now let me explain a bit the picture. If you look at it, this, I don't know if you have been, this is the city of Pittsburgh. I don't know if you can see the picture. Okay, let me stay like this. Right, this is here, if you look, this is downtown here. And here, this is the University of Pittsburgh campus. Here is Pitt and Carnegie Mellon. Both of them are connected. They're like, so here, so they're separated by a street. So I used to live on that street that separates the two campuses. Anyway, and here, if you look at, I don't know, here, do you see this tiny stadium here next to the river? This is where Pittsburgh Steelers used to play. Probably you've heard of Pittsburgh Steelers, right? A famous football team. Yeah, it was a great city. Yeah, the picture, of course, is not taken by me, so. But it's you can find it on Wikipedia. Anyway, from time to time I will change my background so that with some other pictures as well. Okay, I think we can get started now. Well, we have some new people here, which I'm glad that more people. That more people are starting to be interested in. Wait, what's, give me 1 second. Okay. All right, you can see the screen. And like I said, today we're gonna start doing combinatorics. And here I'm gonna do the following. You see, there are plenty of things to cover in combinatorics. Like I said, there is like a 1 semester course, so I'm trying to cover as much as I can. And here there'll be some, so today we'll cover, we'll be talking about binomials and pigeonhole principle. So I'm gonna do the basics. And some of the problems that will appear on the worksheet are from these two topics. Well, like I said, this is just a very tiny portion of what we're supposed to do. And also there are I would say 4 major topics in combinatorics. So the counting, graph theory, there's a whole theory. There's a Ramsey theory where Pigeonhole Principle, it's a part of, it's one of the main tools. And also there is this new method called the probabilistic method. I'm not gonna even touch that, so forget about it. So what I'm trying to do will be to talk about binomials, some identities, and how to use these, and also about pigeonhole principle. And maybe I'll talk about in another lecture about graph theory and maybe a little bit of generating functions, is also a very nice topic to talk about. Okay, now let's start. And I would like to, also I will assume here an induction, which I already covered. So I want to talk about binomials first. And then I will talk about pigeonhole principles, and we'll see some examples. Well, about binomials, you already know that, for example, that, well, for, let's say, n and k, and let's say n greater than k, in fact, greater than 0, we define the following binomial n choose k. So we define n choose k as the following: n squared over k squared times n minus k squared. Oh, squared, Jesus, factorial. Oh my. Right? So this is the definition of the binomial. And now we have the theorem, which is called the binomial theorem, which is very important. Which says the following: for real numbers x and y and integers n, we have that the following. We have that x plus y, everything raised to the power n. As you all know, this is nothing else than the sum of k equals 0 to n of n choose k times x to the k times y to the n minus k, right? So this is the binomial theorem. And from here, well, let me point out some remarks immediately. For example, remarks, because this will be very important when we'll deduce some binomial identities. For example, well, I'm not going to go into the proof of any of this, so I'm not going to stay and do an entire combinatorics class here. So, but I want to point out some remarks. And the first one, some immediate consequence. For example, if we take x to be y to be equal, both of them to be equal to 1, then guess what? We obtain that. So this implies that what? Well, it will imply that the sum from k equals of 0 to n of n choose k is nothing other than 2 to the power n. So this is one of the first identities that you need to know. And for example, if you take, I don't know, maybe x to be 1 and y to be -1, you will get that the sum, this sum, and this time you'll have here -1 to the power k, right? In fact, no, you take the other way around, sorry. You take x to be -1 and y 1. You'll get that this -1 to the k n choose k will be 0. All right. In fact, you'll have even a much more general version of than this. Let's call this the following theorem, which is the multinomial formula, and it's very good when you count. Which says the following: if you for real numbers, let's say x1, x2, xm, and an integer n, we have that, let's write it here, that x1 plus x2 plus xm, everything to the power n, right? So we have, this will be we'll have this sum, and now this sum will be of, over all indices A1, AM, with their sum equals n, and these indices A1, A2, AM will be non-negative, right? And this will be here, as you can imagine, will be n choose A1, A2, AM, x1 to I1, and xm to IM. Anyway, this is just a generalization of the binomial formula, so that's why we have this, but I'm not sure if you can use this in any application, but those of you who have taken a combinatorics class probably have done it. Jack, have you done this in your combinatorics class?
Yeah,
probably.
I did that.
Probably you did. You did it with Dermot, right?
Yeah.
Oh, okay, definitely you did. All right, now another thing that I want to remind you is the following theorem, which is due to, well, we'll call this Pascal's identity. And this is important as well. For integers, let's say nk greater or equal than 2, we have that, and like I said, this is an important identity because I think I'm going to use this in some applications. We have the following: n choose k can be we can break this guy into the following. We can choose into n minus 1 choose k minus 1 plus n minus 1 choose k. So you can do this. And even more general, we'll have the following identity, and I'm going to point out a remark here as well. The theorem. This is what we call Vandermon's identity, or Vandermonde convolution. And in fact, I'm going to use this in some problem today. Yes, I'm going to Vandermonde's identity, which is important. This says the following. So let us consider A, B, and N be positive integers such that both of these guys, A, B, are greater or equal than N. Then we have the following identity. The sum of A choose K times B choose N minus K, right? Is nothing else than just A plus B choose N. So this is the Vandermonde identity, very important. And here, let me point out the following interesting consequence. If A equals B equals N, so let's take them to be equal, then guess what? We will obtain the following. It will follow that what? That the sum, from 0, of these two. Well, if A equals B equals N, we will have what? We will have N choose K times N choose N minus K equals 2N choose N. But here, if you look at this guy, right, these two are equal. So, but also I forgot to mention, but you can actually prove this. N choose K will always be equal with N choose n minus k. So the identity becomes the following: the sum of n choose k squared is 2n choose n. All right, so these are the identities. Well, these are just a couple of them. In fact, let me see if I forgot to mention some of them. Well, there is let me see. So Pascal's identity. Actually, there are some others. Maybe yeah. Let's see some other identities. But actually, you can prove this. That's why I'm not going to stay and prove this. You can find them in any combinatorics course. And in fact, we would like to we would like to do some kind of a partial summation, let's say. I put quotes in this. And the first thing that I have in mind is the following. What if we have something like this? The sum, and this time I'm going to do the following. It's m choose k, you see? And here I'm going to start from k to n, right? Not necessarily to start from 0, right? If I so this would be n plus 1 choose k plus 1. So we will call this upper summation. And another identity, which will be, again, a little bit more general than the one that we mentioned, the sum of these binomials, like m plus k choose k. This will be a little bit more general, so we'll call this parallel summation. So it will be n plus m plus 1 choose n, right? Yeah. And we call this parallel summation. All right. I think this sums up pretty much everything. Well, like I said here, this guy, also this is important, that n choose k is the same as n choose n minus k. And now let's do some problems. And the problems that I have in mind, let me start with something. In fact, there are plenty of problems that I have in mind, but let me start with an easy one, with some old Putnam problems. So problems. So problem 1. This was a Putnam A5, pay attention, 1962. I think I've done a geometry problem from 1962. For some reason, I have a problem with this Putnam from this year. Actually, their problems are really nice, surprisingly. In fact, most of the Putnam problems I looked, there is this website with some old Putnam problems, and some of them are really, really nice. Like even back in the 30s, 40s, I was very surprised and very relevant, I would say. So the problem says the following: find a simple expression well, not involving a sum for the following. And let me write it in this way. 1 squared times n choose 1 plus 2 squared times n choose 2 plus so on plus n squared times n choose n, right? Well, it's quite clear. This is the sum from k equals 1 to n of k squared times n choose k. All right. So that is the problem. I want you to look at it and tell me what do you think? So let's look at it. And you see, there is one thing that I would like to, this problem, in fact, it illustrates quite perfectly some techniques that I want to show you. You know, sometimes when you want to play with these identities and you try to derive them from the binomial theorem, basically, you can, like I said, play around with integration, with the differentiation, for example. Let me be more specific. So in this sense, the problem is tricky, but once you know this technique, there is no way you can miss a problem like this. What do I mean by that? So let's go back to the binomial theorem, but I'm going to write it in this way. So from the binomial theorem, we have that. Let me write it in this way. 1 plus x, let's say, everything to the power n. This will be nothing else than the sum of n choose k times x to the power k, right? So that's what we have from the binomial theorem, right? Remember, we x plus y everything to the power n was the sum of n choose k times x to the k times y to the n minus k, but in this case, y is 1. So we have this. And now we can play around. Imagine this is like you have an x there. So maybe you have seen that if we plug in x to be 1, we get this identity that the sum of n choose k from 0 to n is 2 to the power n. But we can also do some other things. For example, what would you think? Look at the sum. Does this ring a bell to you? Let's play around with it. Let's do it in a naive way. You see, you have the equality of two quantities, right? And both of them are in terms of x. Can you differentiate, for example? Yes, we can, right? So differentiating the equality So we have. So what do we have? So we will have that. This will be n 1 plus x to the power n minus 1 times 1 plus x prime, which is 1, so I have no problems. And this guy will be, so here I'm differentiating term by term, so this will be the sum of k and choose k x to the power k minus 1. Wow, look at it. This is nice. And we can play around here. You see, if you, for example, if you plug in x equals 1, you'll get an identity, but I'm not interested in that because this is not what I'm, okay, let's point out this remark for x equals 1, for example, we get that n times 2 to the power n minus 1 is the sum from k equals 0 to n of k choose n minus k times n choose k is n times 2 to the power n minus 1. But you see, I'm not interested in that. I have a k squared there. Look at this guy. This is not the same as this guy. So maybe I should do something. So how do I get that k squared? What do you think? Maybe, well, I differentiated once, but who tells me that I cannot differentiate twice, right? Right? Let's differentiate again. So this is not what I want, which is not what we want, what we exactly want. But anyway, it's a nice identity. But maybe, so let's call this star here. So differentiating star again. We have, let's see, what do we have? So we have that n, let's look at star. So we have n times n minus 1 times 1 plus x to the power n minus 2 will be equal to the sum from, so again here we differentiate term by term, will be k times k minus 1 and choose k x to the power k minus 2, right? So we have this. And this guy, let's write it, is nothing else than just the sum k squared minus k and choose k x to the k minus 2. Well, but if I plug in x equals 1 now, that's still not exactly what I want, right? But we can write this in a certain way. So what should we do from here? You see, I have, look at this term here. I have a k squared here, and I have a k here. I have a combination of two. So maybe I should do something about it. You see, but I have the difference. So what if we take x to be 1 here? Let's see what happens. So from here, for x equals 1, we got this. So we should keep this in mind. Let me circle this. And now for x equals 1, we have, let's see, so we have n times n minus 1 times 2 to the power n minus 2 will be the sum k squared minus k, and choose k, right? So we have this. Now let me circle this. We have these two identities. Look at them. Well, both of them here. Now the question is, can you write your problem in terms of these two? Look at them very, very carefully. Well, if you would do what? If you add them up, right? Let's say this is 1 here, and this is 2 here. If you add them up, right, this negative k here will disappear. And so adding 1 and 2, right? 1 and 2 will give us the following. Let's see. N to the power 2 minus 2, n times 2 to the n minus 1 plus n times n minus 1 times 2 to the n minus 2 will be the sum. So the first one was k plus this sum here. And this will be equal to, well, when you add these two, it will give us nothing else than just what we want. K squared times n choose k, which is exactly, wait. Well, let's be careful here a bit. You see, where am I not careful here? You see, with the summation, right? Because it will start from, well, if you want from k equals 0, but if you plug in for k 0, right, you'll get nothing. So it's the same as the sum 1 squared times n choose 1 plus 2 squared times n choose 2 plus n squared times n choose n. And that's what we want to prove, right? If we go back, that's exactly what we want to prove. And that's it. So let me write it again. We have that, and we can factor here some numbers. So 1 squared times n choose 1 plus 2 squared times n choose 2 plus n squared times n choose n is nothing else than just, if you factor this guy there, this will be anyway, this would be what? This should be n times n plus 1 times 2 to the n minus 2. Yes, 2 to the n minus 2. Please correct me if I'm doing some stupid algebra mistake, but probably. And that's it. So that's one way to derive this kind of identities. Is it clear for everybody? So it wasn't a big deal. For example, you can do something similar. Probably I shouldn't spend time with this, but let me point out a remark. But I want because I want to talk about Pigeonhole Principle as well. And I do some other problems also. For example, in a similar fashion, try to evaluate this sum here. So try to evaluate this sum. You can see a -1 to the power k, k to the n times 2n choose k. Well, here it's something similar. So you have to start, as you can see, you have there, let me give you the hint. Well, it will be more complicated, but you start with the binomial expansion of 1 plus x, and now you raise this guy everything to the power 2n, right? So this is how we're gonna, you use the binomial expansion, right, of this. And then at some point you will have, imagine that this is again a function, and then you start differentiating. And of course you'll take x to be -1 because you also want to get your -1 to the power k coefficient. And then you start differentiating. Once you have x, then you take x to be -1, and then you keep going and you keep going, and then at some point you'll derive something. Anyway, this is a nice identity. And now I would like to do another problem. In fact, let me do another Putnam problem. So problem 2. I have a couple of them, so this was a Putnam B2 in 1992, something more recent, which says the following. Show that the coefficient of x to the k, so pay attention here, in the expansion, and here we will have the expansion of the following, of 1 plus x squared plus x cubed, everything to the power n. Wow, that's quite an expansion. Yes, is the following. It will be this sum from j equals 0 to n of n choose j times n choose n minus 2j. There's, wait, sorry. So j, okay, because it's k here, let's not mess things around. And here will be k minus 2j. Okay. Look at it for a couple of minutes. Yeah, look at it for a minute, just a second. So you will be tempted to do something, right? What would you do? I'm actually curious.
Try to use like the multinomial formula.
Yes, that would be an idea, but can you imagine? My goodness, that would be the sum of, oh my God, that would be, that would be the sum of, you have, how many indices you will have there? You'll have like 4, right? Yeah, that would be an idea, but I would not adventure myself into that, into those computations. So let's try something that will avoid that. Maybe I could break this into 2 parts, right? Can I do this? That is the question. And if you look at this expansion, so first, we look at this guy, 1 plus x squared plus x cubed, everything to the power n. And let's be careful here when we look at this guy. Well, can we factor something there? As you can see, I can factor 1 plus x, right? Look at this guy, 1 plus x. Let's group these two guys together. Here I can factor an x squared actually, times 1 plus x, everything to the power n. And this guy will be nothing else than what? Will be 1 plus x times 1 plus x squared, everything to the power n. So this is nothing else than just 1 plus x to the power n times 1 plus x squared to the power n. Wow, that's beautiful. Now let's expand each one of them. And if we do this, let's use the binomial formula for each one of them. And I'm gonna use the following. So the first one will be from, let's use this index I. So it will be the sum over all i's of n choose I, x to the I. And let's, for the second one, let's choose 101. So j will be not a good choice. Let's put I prime over all n choose I prime, x to the power, well, wait, let's be careful here. This is 2I prime, right? Because it's squared there, so this will be x to the power 2I prime. Oh my. Right? By the binomial formula. Okay. All right, and now, well, how do we get this term? You see, now we have to multiply these two. You see, if I'm interested to get the coefficient of x to the k. So how do I get the x to the k term? So the question is, how do we get the x to the k term? That is the question in this expansion, right? So will be the product of what? Can you tell me? Right? Will be the pairing of what? Of n choose I, right? X to the I. That would be the term. And pay attention here. So with the second one, this will be important. So the answer is that we get the x to the k term by, and now we should do a pairing, by pairing, let's say. And now let's look. We pair the, by pairing each and choose I, x to the I, right? Right, we take each one of them from the first sum, right? This, when I mean the first sum is this one here. This is the first sum. All right, and this will be the second sum. From the first sum, and now with what? With, and pay attention here because I want to have, so x to the k. So with what term here will be n, choose what? K minus 2i, right? Right? Times x to the k minus 2i from the second sum. Well, it's quite clear because look at what you have to prove. So, and so the coefficient will be the product, or the sum of the product of these two. So the coefficient, when you multiply these two sum, it's quite clear. So the coefficient is nothing else, the coefficient of x to the k, let's say, is the product well, in the product, sorry, in the product is given by the sum from k equals, okay, so from I equals 0 to k, I equals 0 to k of what? So we're gonna, this is the product of this, so you'll have n choose I times n choose k minus 2i, right? And that's it. We're done. That was a problem. You know, the only thing you had to do is just to look at these two sums. So that was not that's it. So that's the problem. Now let me. There was another Putnam problem. In fact, there are plenty of them, but there was another recent one that I had in mind. I think it was from one of my homework problems. Let me look it up. Give me a second. I think it was on my, it was an inequality that I would like to do, and I put it in my homework. And well, it was in my algebra because, well, it uses binomials. Give me 1 second. The problem says the following. Okay, here we go. So problem 3. And after, okay, problem 3, so this was a Putnam B2 2004. Again, so an easy one. Let m and n be positive integers. show that m plus n factorial over m plus n, everything to the power m plus n, is less than m factorial over m to the power m times n factorial over n to the power n. Well, look at it. Let's, I want you to look at it for a bit. Well, there are plenty of ways to do this problem. So, in fact, well, when we will talk about integrals, you will see that this is nothing. This is just a consequence of the Euler beta function. But anyway, I don't want to go there. But why would I say this is so standard? Well, because the only thing you need to take care of, you see, maybe the statement looks a bit scary, but it's not that scary as you think. If you look at it, the only thing you need to take care of is this guy, right? Because you know how m plus n factorial, it is what it is, you can see it. The only thing is that you cannot see that guy, m plus n. And let me give you, in fact, I'm going to give you the sketch, and I'll leave the details to you. I want you to do it by yourself. So the only thing you need to do is, by the binomial theorem, show that m plus n, and you raise this everything to the power m plus n. So you expand over m plus n in the binomial theorem. So once you expand this and you have all this sum and you neglect all terms except this one, where you have this coefficient m plus n, choose m times m to the power m times n to the power n. So just expand the binomial theorem, and that's it. And then once you use this, the inequality will become obvious. Anyway, that's it. And you know, you can fill in the details, but I can say one thing, and the devil is in the details. So I will let you deal with that. I'm sure you can handle the devil in these details here. Okay. Now, there was one more problem that I wanted to do. It was a Putnam, let me see. It was a Putnam, again in 1965, I think. Let me look it up. I don't recall all the statements, but I remember it was, all right. So again, an identity which says something like this. So another problem 4. This was Putnam A2, again in the similar fashion, 1965, wow, which says the following: show that for any positive integer n, we have the following, that this sum, and I want you to, from R from 0 to n integer part n minus 1 over 2, well, of the following quantity, then I'm going to put it in this way, or maybe no, I should put it in this way. N minus 2r, everything over n choose r, everything squared, okay, is 1 over n times 2n minus 2, choose n minus 1. Oh my. Okay, I want you to look at it. Yeah, that's the problem. Anyway, I did not recall the exact statement, but I remember this was a nice one because it kind of rings a bell. And if you look here, let me just give you the sketch, and I'll leave it to you to fill in the details. Because it's quite clear what to do once you see this. Look at the statement. Now let's substitute, just to, let's substitute, because I want to get rid of this guy, n minus r to be equal to a number s. So if we substitute this in the given summation, right, then we will have that, then our sum is the following. So we'll have this from r equals 0 to n, right, of this guy, n minus 2r over n times n choose r squared. And now we can play around with this. We'll do some computations, and after some computations, this will be equal to, so here I'll leave computations to you. So this will be equal to some, okay, let me see, will be to, okay, I'm not going to be precise here, some n choose r squared, right, minus some n choose minus some coefficient, I don't know, 4 I think it was, again, and I have here r over n choose r squared, and some others. Anyway, but the only, but at some point, once you do the computations, the main ingredients here were the following two identities. So the main ingredients are the identities. Well, one of them is the Vandermonde identity. Well, let me put one, which is the sum, this sum, and choose r squared. You already know what this is. This is 2n choose n. And the second one, when we have this sum, let's say m, so the Vandermonde identity, m choose k minus r times n choose r. This would be nothing else than just m plus n choose k. And here we sum up from r 0 to k, right? This is the Vandermonde identity. And you use these two identities, and at some point you can compute this. Anyway, and it will give you this. I'm not going to go into the details with this problem. I'm going to leave it to you. Now, I want to veer towards Pigeonhole Principle. This is very, very important. Oh my goodness, and I don't have too much time, but anyway, maybe I'll go over time. I think you kind of got the gist of what's going on with the binomials, right? Do you have any questions? Is everything clear? Well, more or less. Jack? Aaron?
Yeah, looks good.
All right. Abby, is everything clear? Okay. Now let's talk about the pigeonhole principle. And this is nothing else than just a basic observation, but anyway, I'm going to write it in a fancy way. It says the following. So it's a basic observation. If n pigeons are divided over, let's say, over strictly fewer, let's say, well, I usually have this, I put them in m boxes or n plus 1 boxes, so there exists at least one box with 2 pigeons in it. But anyway, let's let's write it in this way. So are divided over strictly fewer than n boxes, right? There will be a box containing at least 2 pigeons, right? Is this clear? That's what it is. So, and now if we want to put it in a fancy way, it says the following. Well, let's call this proposition. Let's write this in a mathematical way. Let's consider 2 finite sets. Let x and I be finite sets. And we will consider this function f from x to y, right? And if the cardinality of f of x is strictly larger than y, then there exists 2 elements in the set x such that f of a, so let's call these 2 elements a and b, such that f of a is f of b, right? Well, in other words, so let me point out a remark. In other words, if f defined from x to y is an injective function, is a one-to-one function, or injective function, then the cardinality of x will be less or equal than the cardinality of y. And you know, there is this theorem which says that if I have a from a finite set to another finite set, if it's injective, if and only if, then it's also surjective. All right, let me give you some quick examples of how do we apply the pigeonhole principle. For example, some quick examples. Let me see. One. For example, among 13 people, so any way you pick, you choose 13 people, at least 2 of them two of them share the same birth month, right? They have the same sign. There is no way you can, because there are only 12 of them. So, right? You label the boxes as 12, and the pigeons are the people. So the boxes are only 12, but you have more than that. You have 13. So two of them will be in the same box. So we'll have the same birth month. Another example. Suppose that 5 pairs. Okay, this is a nice example of socks are in a drawer. By picking six socks, we have at least one. We choose at least one pair. At least one pair. Right? So you label the boxes by the pairs, right? You have like red pair, blue pair, whatever. And you put the 6 socks into the boxes according to the description, and that's it. Anyway, and you can go and with plenty of other examples. Well, let me do some other examples, maybe some basic ones. In fact, there will be more problems, but let me do this one. Okay, let me do this. So another example, let's call this problem. So suppose I'm going to draw up directly a, so we have a triangle in an equilateral triangle, right? So these are equal. So this is of side length 1, right? So let's label this. So we have a triangle ABC is equilateral. And suppose we have 5 points inside and on the boundary of the triangle. So let's look, let's put these 5 points here. Let's say we have here 1, 2, 3, 4, and you can put anywhere you want, 5. Put it here. Right? You have 5 points. Show that there exists at least 2 of them such that their distance is at most 1/2. Okay. I want you to think of this. This is a basic application. of Pigeonhole. So how would you approach this problem?
You could try dividing the triangle up into smaller triangle boxes.
Exactly. So we should, but how do we divide the triangle? That is a question.
Can we use haste?
Say that again, Anna. So we try to divide this triangle into something that will look the same, right? How should we do this?
Can we use haste?
I don't understand. What do you mean? H, the altitude of the triangle. That's what you mean? No, that would be, so yeah, but when you do, let me see. So when you, okay, you take the altitude, let's say from A, but how do you know that you can divide, okay, this is the altitude, but how do you know you have divided your triangle in equal parts? That is the question, right? So you don't know that. So maybe there is something, maybe there is a smarter way for me to partition this equilateral triangle. Keep that in mind. Let me give you the idea. What if we consider the midpoints? Look here. Let's say M, N, and P. So consider the midpoints M and P of BC, CA, and AB. Well, what can you tell me now? Look at the triangle.
Each triangle has like the same area.
So they're basically kind of the same, right? Look at them. How many triangles do I have? They're congruent, right? So how many triangles do I have?
4.
Exactly. I have 1, 2, 3, and 4 triangles. Let's say call them T1, T2, T3, and T4. So we have 4. So in this way, we obtained um, 4 congruent triangles. Right, but they're basically the same. Well, what is the sine length of each triangle? It's 1/2, correct? right? Congruent triangles of side length 1/2. All right, that's great. How many points do I have? And how many triangles do I have? How many points? 5. How many triangles? 4. So by the pigeonhole principle, it follows what? That there exist at least 2 points in one of the inside one of the triangles. So by the pigeonhole principle,
And those 2 points will have a distance between one another less than 1/2.
yes, it's less than the side length of the, right? There exists at least 2 points inside and on the boundary, or on the boundary of one of the triangles. You see, in the combinatorics, you have to write a lot. And one of the triangles, T1, T2, T3, T4. It doesn't matter which one. If you see, even if I look here, and what is the maximal distance? It's 1/2, right? For example, if you place one here and one here, they cannot be more than, look here. Then the side length of, for example, you see, you have these two, right?
She said they could be on the boundary though, so you could be exactly
Yeah,
1/2.
you can put one here and one here, but right?
I couldn't see where you're pointing to on the screen.
Say that again.
I said I couldn't see where you're pointing to on the screen.
Look, for example, you can have them here. One
okay,
here
yeah,
and one here. So,
gotcha.
so it will be just this is what I mean on the boundary. But anyway, like I said, there exist at least 2 points. That's it. Because one can say like, look, but I have this guy here and I have this guy here, but wait, they're not in the same triangle, right? Look at this. If I draw this, well, it's larger than 1/2, but guess what? They're not in the same triangle. So like I said, 2 points on the inside on one of the triangles. But the distance of these 2 points is at most 1/2.
What are the odds that there's a pigeonhole principle question on the Putnam?
Oh, very high. In fact, unfortunately, I didn't have, you will see in the homework, when we're on Thursday in the recitation, you will see plenty of problems using pigeonhole principle. So I will, and also I'll do another lecture when I will solve more problems using pigeonhole principle and some other topics. But anyway, so the distance of these 2 points is at most 1/2, which is the side length of the triangles of one of the triangles. In fact, of the triangles TK, right? From K equals 1 to 4. Anyway, and that's it. So you prove that there exist at least 2. Pay attention. It's not like the distance of any 2. No, there exists at least 2, and that's it. So as you see, the main thing is to consider the midpoints. That was the trick here. Anyway, I will stop here. I hope you got the idea of how to use the pigeonhole principle. Next time I will do another lecture, probably tomorrow, And I will, I will present more applications of the pigeonhole principle so that you can get because at first when you see it for the first time, it's kind of like, oh, you'll be like, wow, you cannot believe this has applications like this. I remember when I saw it for the first time, I think it was in my 8th grade or something like this. I was like, wow, that's impressive. But still, you have to get accustomed to it. All right, guys, I'll stop here. Thank you very much.